So often when I tell people what I do, that I research mathematics, they recoil in some combination of horror and disgust. Research math, they'll ask, like finding new numbers? No, not exactly. What math research really is all about is identifying a problem you care about and distilling that problem down to its fundamental characteristics via mathematical modeling, and then applying quantitative tools like arithmetic and calculus and formal logic to derive objectively true conclusions. So I have a problem. My problem is that I like quantum mechanics, but I'm not very good at quantum mechanics. And so instead I pretend to study quantum mechanics. In particular, I study a simple model for how quantum particles interact with media in space. Now, as a mathematician, I need to define all of those words that I've just told you. So let's talk about the elements of a model. So I need to tell you what I mean by space, what I mean when I say a material, and what I mean when I say a quantum particle, and what exactly I mean when I say interacts. And so this is why I say that I pretend to study quantum physics. So for me, space consists of a system of infinitely many points in a line. In the quantum world, this isn't so far from the truth. Things are roughly discrete. And by a material, I mean a description of how attractive each of those points is to quantum particles. Think about hills and valleys. And by a quantum particle, well, in the quantum world, uncertainty reigns. And so you really need, when you're describing a quantum particle, to describe the probability of observing it at a certain spot. And last but not least, and this is why I can at least say I pretend to study physics, we assume that these particles evolve according to the famous Schrodinger equation. Now, don't panic. This is a very frightening equation, and if you don't remember what I or this squirrely D means, I just want you to focus on the right-hand side of this equation, this bold H. So this stands for Hamiltonian, and it's simply a rule that assigns to a quantum particle its energy in space. And it encompasses every aspect of the problem that we focus on. So I study these Hamiltonians. So how do you study a Hamiltonian? Well, you take your material, and as Jamal told us, you bombard it with millions and millions and millions of particles, and then you see the energies that are reflected and absorbed. And this information is called the spectrum, the energy spectrum of your Hamiltonian. And I study isospectral dynamics. Iso meaning same, spectral meaning spectrum, and dynamics meaning change. How can I change the Hamiltonian without changing the spectrum? So what did I prove? So often math physicists assume that your Hamiltonian looks like a material in a vacuum. So you really are measuring just free kinetic energy of the particle without any forces acting on it, and then some potential energy. And what I asked is, from a spectral perspective, is this a good assumption? And it turns out that if you assume your Hamiltonian is conductive, meaning that your quantum particles sort of pass through it in time, no. Most spectra actually don't come from Hamiltonians like this. You really need to incorporate some sort of local acceleration, a force field. And I can prove this for you in about 30 seconds. So for a typical spectrum, every isospectral Hamiltonian that's conductive can be approximated by just moving around. And this never introduces a force field. What I showed is that there's another isospectral move called the toe-to flow that always introduces a force field. And therefore, it cannot be the case that a typical spectrum comes from one of these materials in a vacuum. And as with any science, when you answer a question, 3 more pop up. So exactly how atypical are these kinds of Hamiltonians? Are there other isospectral moves we can study, and what do you learn from them? And then I snuck this word conductive in. Can we extend this theory beyond these conductive Hamiltonians? And I have active research going on in all 3 of these areas, but what I really want to focus on, and what I want you to take away from this talk, is not my mathematics, but why mathematics. So why do mathematicians choose to study the world without sort of observing these beautiful things that we can, and instead by turning inwards? And the reason is we want to develop a bottom-up understanding of the world. We want to assume the very minimal, fundamental things that describe our world, and then build the world out of these. It's a difference between creation and observation. And with this comes a degree of certainty. You actually have 0 p-value, and this gives you absolute beauty in your results. And honestly, this approach really can be fun. That said, if you do know where I can find some new numbers, you should tell me afterwards. Thank you very much.